Hello everyone and welcome back to the OpenGL 3D game tutorial series. In this fifth episode, we will see how to create simple animations in OpenGL. In particular, we will see how to draw a quadrilateral mesh, how to create and use an uniform buffer object in order to pass data from CPU to GPU, and in the end, how to use those data in the shaders in such a way to create visual effects like zoom in and zoom out. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to create simple animations in OpenGL. Let's start with the requirements. We need a C++ IDE. In this series we use Visual Studio on Windows and Qt Creator on macOS and Linux. The target platforms are Windows, macOS and Linux. The target graphics API is OpenGL, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. What's the problem to solve today? We want to create animations in OpenGL. In particular, we want to create a zoom in and zoom out effect, like this one. In order to create such effect, in our vertex shader we have to multiply the position with some value. For example, if we multiply the position with 1.0, nothing happens. If we multiply it with 0.5, the polygon is reduced. If instead we use a value of 1.5, the polygon is enlarged. This kind of value can be called scale. This scaling effect can be obtained immediately by writing the value directly in the shader code, but in this way we don't have any animation. In order to get any sort of animation, we have to compute the scale value through the CPU, as so in our C++ code. And then we have to pass it to the GPU, in few words, to our shader code. This data transfer can be done through the so-called uniform buffer object. In few words, uniform buffer object is nothing more than a memory buffer that resides on video memory that allows CPU to pass data to the GPU. So, in order to create our zoom in and zoom out animation, we have to create the OUniformBuffer class, compute the scale value in such a way it changes at each frame, and to do that we have to introduce the so-called delta time, a value that indicates the elapsed seconds from the previous frame, and then we have to take the scale value and send it to the uniform buffer, in such a way the vertex shader can take it and transform the vertex position. If you have questions, doubts or comments about this topic, don't hesitate to leave them in the comment section of this video or in the Discord server. The link to the Discord server is available in the video description. Also, if you find these tutorials helpful, please consider to support their development on Patreon. Every single contribution makes the difference, regardless the amount. Very well, we have gathered all the necessary information to start the implementation. As first thing, let's draw the quadrilateral mesh. So let's go to our graphics engine header file, and in the draw triangles method we have to add a new parameter that should indicate the way in which the vertices are placed inside the vertex buffer. Let's go to our prerequisites header file, and here let's add a new enumerator called OTriangleType. We have two modes to add here, the triangle list and triangle strip. In triangle list mode, the vertices in the vertex buffer are placed in such a way to form a list of groups of 3 vertices, where each of these 3 vertices will be used to draw a triangle. In triangle strip mode, instead, the vertices are placed one after the other. The first 3 vertices are used to draw the first triangle. From the 4th vertex onwards, at each vertex added, a triangle is drawn. We are going to use the triangle strip mode to draw our quadrilateral polygon. Let's use this enum to add the new parameter. And of course, let's implement it. Now it's the time to go to OGame class and we have to start to fill our vertex array object with the vertices for our quadrilateral. In this case, we have to do nothing more than to add a new vertex and displace the previous vertices in the way shown in the image. Let's also rename the triangle vertices variable in polygon vertices. At this point, let's pass the triangle strip value in the drawTriangles method. Let's see if it works. And it works. The next step to do is to add the OUniformBuffer class. The class is very similar to the classes added previously, so we have to add the constructor and destructor, we have to define the ID attribute, and retrieve it with getID method. Now let's start to implement these methods. As usual, let's include the GLED header file. And in the constructor, let's start to create our uniform buffer. So, we have to use the GLGen buffers in the same way we have seen with vertex buffer. Let's call GLBindBuffer in such a way the next GL functions called act towards this buffer. Then let's call GLBufferData that allows to define the data inside the uniform buffer. In particular here we want to define its size in memory. To do that we have to pass the size through the constructor. For this purpose, let's add a new descriptor in our prerequisites and let's call it OUniformBufferDesc. And let's add size as attribute. Very well, let's use it in the constructor. Finally, let's pass the size in GLBufferData. In the end, let's unbind this buffer from graphics pipeline. Don't forget to store the size attribute that we will use later. At this point, let's finish the work by implementing getID and by calling GLDeleteBuffers in the destructor. So far, so good. Now we have to create the uniform buffer from graphics engine. The implementation of this method is the same one done for the previous object. We have to define its shared pointer in OpenRequisites header file. Add the createUniformBuffer method in graphics engine class, adding the descriptor as parameter. And in the C++ file, we have to call again makeShared in order to create the shared pointer object. That's all. The next thing to do is to go to OGame class. Here we have to rename the VAO to Polygon VAO. At this point, let's start to create the uniform buffer. In order to create this buffer, we have to define the data structure we want to send from the CPU to the GPU, as we have seen in the introduction. Since we want to send a scale factor of type float, let's define here a structure called uniform data, and let's add a float variable called scale. And in the descriptor, let's pass the size of the uniform data structure. In the end, let's store the uniform buffer inside an attribute. Very good! It's arrived the time to see how to use this data structure inside the vertex shader. So let's copy paste this structure inside vertex shader. That's it, we have only to convert a struct in uniform and F32 in float. In order to make the scaling effect, let's multiply the scale value with the position. What's next? Well, in order to bind a uniform buffer to a shader, we have to add a method inside our shader program class called setUniformBufferSlot. This function should allow the user to define a slot for a specific uniform buffer recognized by the name defined in the shader code. The slot defined here, that is simply a number, will be used later by the graphics pipeline to link the uniform buffer to the shader. All this can be done by calling the glGetUniformBlockIndex and glUniformBlockBinding functions. Now we have to go to our game class, and here we have to call the setUniformBufferSlot method. Let's pass the uniform buffer name defined in the shader code. So uniform data. And let's set a slot number, in this case 0. The last thing to do is to bind the uniform buffer to the graphics pipeline. So let's go to our graphics engine class and let's add a setUniformBuffer method. Where we have to pass the buffer pointer together with the slot number. Let's implement this method, and here we have to call the glBindBufferBase, in which we pass the type of buffer we want to use, the slot number, and the ID of the buffer. Very well, let's use this method in our game class. And let's pass the buffer pointer and the slot number, the same one defined in setUniformBufferSlot, so 0. What else? Well, we have to send the scale data to the shader. We can do that by adding a setData method in our OUniformBuffer class. Let's also add a parameter of type void pointer. This allows us to pass any sort of data structure. In the C++ file, let's call as always glBindBuffer. Then let's call glBufferSubData. This function is not the same as glBufferData because this particular function allows to update an already created buffer with new data. Let's use the size stored during the creation, and that's all. Obviously, at the end, let's unbind the buffer. Let's come back to OGame class, and here we have to define a new object of type uniform data. Let's define the scale to 1.0. At this point, we can pass this data to uniform buffer through the setData method. And that's all. Let's see if it works. And it works. Obviously the quadrilateral is the same because we have multiplied the position of the various vertices with 1. Let's multiply it now with 0.5. At this point the quadrilateral is reduced. If we change now the scale with 1.5 or 2.5, the quadrilateral is enlarged. So far so good. We are ready to make some animation. To do that, we have to introduce the computing of delta time. As we have already seen in the introduction, delta time is the elapsed seconds between the processing of the previous frame and the current one. To compute it, let's use the chronolib of the standard C++. The first thing to do is to get the current time with the now function. Then we have to define an elapsed seconds variable of type chrono duration. At this point, the elapsed seconds is nothing more than the difference between the current time and the previous time. Of course, we have to store the previous time in a suitable attribute of type timePoint. Obviously, we have to make this difference if and only if the previous time has been already initialized with some value. In the end, let's store the current time as previous time for the next frame. The only thing that remains to do is to retrieve the delta time. With delta time, we have all the ingredients to make a simple animation. Let's add a scale attribute inside our game class. And at each frame, let's add to it a 3.14 value multiplied by delta time. This formula allows to reach a value of 3.14 in a second. We have nearly finished. To make the zoom in zoom out effect, we have to apply some kind of function to the scale attribute, like scene, for example. And in order to make the value of scene always positive, let's apply also the absolute function. In the end, let's pass the result to uniform data. Let's see if it works. And it works! This animation runs at 180 degrees at second. Let's apply now 45 degrees. And of course, the animation is slower now. If we apply instead 360 degrees, the animation goes faster. That's all for now, folks. Today we have seen how to make basic animations in OpenGL. The next time we will see how to create and use the metrics. I hope you enjoyed this video. See you soon. Thanks for watching.